Hey everybody! In this video we're going to talk a little bit about coordination chemistry and coordination compounds and what they are. So we're going to do a little bit of introducing some terminology and just looking at stuff kind of in general. And then in subsequent videos we'll get into a little bit more detail about naming and some isomerism and things like that. But the first thing that we want to do is we want to understand what a coordination compound is. So a coordination compound uses a special kind of covalent bond. Remember that covalent bonds, back when we did stuff in the previous chemistry class, covalent bonds were bonds formed by sharing electrons. And so a coordinate covalent bond is a bond that is made between some metal ion, and it's either an anion or a polar molecule. If it's a polar molecule, it's called a ligand. Okay, and so what happens is the electron on the anion or the polar molecule will donate both the electrons in the bond as opposed to them sharing them equally. And so that's what makes a coordinate covalent bond different from a regular covalent bond. So for example, here is this compound right here. This is iron pentacarbonyl. Okay, so here's what happens. So you have an iron ion. Okay, or actually this is an iron atom. Okay, more on that later. But what happens is this compound, carbon monoxide, which turns into what we call carbonyl, will take its electrons, its free electrons here, and it will create the bond between the iron atom and the carbonyl. So that becomes a coordinate covalent bond. And then there's obviously, because there's 5 here, there's 5 of them around this atom. Okay. Now, sometimes you end up with what we call a complex ion. And that's when the coordinate covalent bond is part of an ion, which is then, in essence, part of a greater compound. So here, in this second example, I have this guy. Okay, so this is a complex ion because this thing has coordinate covalent bonds in it. So again, you have platinum, which is the atom, and then around it you have the chloride ion, which in this case the chloride ion is giving both electrons in the to make the bond. And so then that's surrounded by 6 chloride ions, and then the potassium ion is attracted to this because this overall thing is a 2 minus charge, and then each potassium is attracted to that, just like in regular ionic compounds. So what this does is it kind of makes what we learned about ionic bonding and covalent bonding. It kind of turns it up a notch. Okay, and so some of the things that we should maybe be familiar with is this thing over here, and this shows some of the charges on the transition metals. Okay, so in previous classes, you may know that iron is pretty easily a 2 plus or a 3 plus, but we don't know, or you may not know, that iron can also be a 6 plus or a 4 plus or a 5 plus. Okay, so I kind of went in order, but that's what these red ones are. In ionic compounds, you'll see these pretty regularly. Copper is a 1 plus and a 2 plus, but in coordinate covalent compounds or in complex ions, you'll see copper is a 3 plus. Okay, now we're not going to have to memorize all these charges, But I wanted you to see that these coordinate covalent compounds can have transition metals that have all sorts of different charges, okay, or what we would call oxidation states. A ligand is the thing that is attached to a, like we have back here, is the anion or polar molecule that is attached to the transition metal, okay? So, and it is always a Lewis base, okay? And a Lewis base is defined as a base, something that donates a pair of electrons, okay? An acid accepts a pair of electrons. Okay, so because the coordinate covalent bond is made by the ligand donating its 2 electrons, it must have an unshared pair of electrons in order to be considered a ligand. Okay, and so that's something that you'll see. The donor atom is the atom in the compound that has the unshared pair of electrons that makes the coordinate covalent bond. So ammonia, like this guy right here, ammonia is the donor atom. Hydrogen can never be a donor atom because it only has one electron. It can never have a pair of electrons to actually donate to become the donor atom. Okay, so anything that you see that has a pair of electrons can eventually be what we call the donor atom, and more broadly, looking at the whole structure, could be the whole thing could be a ligand that goes onto these coordination compounds. So, obviously chloride, you can see the electron pairs. Cyanide ion, that should be something that's familiar to you. Maybe not thiocyanate so much, but even water. If you look, here is water, which has 2 unshared pairs of electrons. That's pretty good to become what we call a ligand, right? And that oxygen is the donor ion. Now, some of these are pretty interesting. So here's ethylene diamine. Okay, this is what we call a bidentate ion or a bidentate ligand. And so we can break this down into its roots. Bi meaning 2, dent meaning teeth or bite. And so if we look at this, there is 1, 2 nitrogen atoms. And there's no difference between those nitrogen atoms because it's a symmetrical compound and everything like that. So if we have some sort of metal, ethylene diamine will bite on one side of it, and then you'll have the carbon, and then you'll have the nitrogen, and it will bite on the other side of it. So that makes it bidentate. It kind of loops around and makes this fan blade here. Okay, and so that's where we get bidentate from. Okay, so there's a couple of ions that are bidentate, or a couple of ligands that are bidentate. And then polydentate, okay, is something that can bite in several places, more than just one. If you look at, or more than just 2, EDTA is a very common example where you have oxygen atoms all over the place that can latch onto a metal ion, for example. In general, this will latch on in 4 places, okay, on each of these single bonded oxygens, making this a tetradentate ligand. But EDTA is definitely an interesting ligand when we were trying to draw it out. So, and there's a few things more about coordination compounds that we look at, and one of them is the coordination number. Okay, and so the coordination number just tells you how many donor atoms are around the metal atom that's in the complex ion or the coordination compound. So if you have the metal and you have 4 donor ions or 4 donor atoms around it, that has a coordination number of 4. Now it doesn't matter if it's like ethylene diamine and these two things are connected. It still counts as two different donor atoms. And so it's because we're looking at the metal. So the coordination number is based on the metal. So there's 4 places of coordination. The most common numbers are 4 and 6. You'll see that a lot. But then you can also have 2 and 5. They're a little more, a little harder to come by. And I don't know if I've ever seen anything with 3, but I'm sure they exist somewhere. Okay. So if we look at this compound here, or this is not a compound. This isn't a compound. This is a complex ion. Okay. It has a metal, and then it has these ammonia compounds stuck to it. And so this makes this a complex ion. Okay, so let me show you what its coordination number is here. Okay, so if we have copper as our metal here, we are going to have an NH3 here, an NH3 here, an N with 3 H's here, and an NH3 here. So if we look, that's a 1, 2, 3, 4. That has a coordination number of 4. Okay. So, and again, this whole thing, let me make sure that I draw this correctly, has a charge of 2+, so we put that in brackets and put a 2+ around it. Okay, and I already explained what bidentate and polydentate ligands are, and I also explained how they work in determining the coordination number. But one of the things that we can do is we can determine the oxidation numbers of metals, because we know now all the information, kind of all the stuff surrounding the metal, the ligands or the ions that are dealing with it. So we can actually figure out oxidation states or oxidation numbers or charges, whatever you want to call it. Okay, technically it's not a charge, even though that's kind of what chemists go to, because it's a covalent bond. We can't have a charge in a covalent bond. This is a charge, but when we're talking about copper, because this is a coordinate covalent bond, we can't assign a charge to it. We have to assign an oxidation state to it. So anyways, we can determine the oxidation state of some central atoms, but we need to know a couple of things in order to do this. And these things we need to know from previous learning. It's not something that we went through in this video necessarily. Okay, so if we wanted to find what the charge of that ruthenium atom is, okay, well, what we know is this thing is split up into 2 parts. We have this ion and this ion. So this is the positive side of this, and this is the negative side. So what we know is, because we have 2 chlorine atoms, that this is a Cl, that's Cl2. So we know that in order to cancel out the other side, that this must be a 2+ ion. So Ru parenthesis NH3 5 H2O must be a 2+ ion. Okay, and we almost always surround a complex ion with square brackets. Okay, so now what is the charge on the metal? Okay, well, in order to do that, we kind of have to work backwards. What's the charge on water? Well, water has a 0 charge. And what's the charge on ammonia? Ammonia has a 0 charge. These are neutral these are neutral compounds, but they're ligands because, remember, nitrogen has an unshared pair of electrons. Water has, the oxygen on it has unshared pairs of electrons. So if this is 0 and this is 0, the only way that this can add up to 2+ is if the ruthenium is 2+. Okay, so now if we look at this again, if we look at another one, okay, which is this guy. Okay, again, we have to kind of work backwards here. Again, we have two parts. We have the positive side, and we have the negative side. So we have CrNH3, 6. And then we have NO3, but we have 3 of those. And so we should know that the charge on the nitrate ion is minus. Okay, and since there's 3 of them, this guy should be 3 minus. So that makes the charge on this ion, the whole thing, 3 plus. And now again, we work backwards. So we're just kind of working backwards until we get to the metal. And so again, ammonia, because it's a compound, and in this case is a ligand, this has a 0 charge. Okay, I know it seems strange that we're bonding with things that don't have a charge, but that happens all the time in covalent compounds, right? When you think of, putting like in methane, right? This bond is happening not because they're charged, it's happening because they're sharing electrons. Well, that's kind of what's happening here. This thing isn't charged, it's just sharing electrons. So it's a 0 charge. So that makes the oxidation state of this, since it has to add up to 3 plus, has to be 3 plus. Okay, so let's do this last one. So this is iron pentacarbonyl. Okay, so FeCO5. This is a strange one because there's not really anything that seems to be an ion right away. And so what we know is this thing. This is carbon monoxide. But carbon monoxide, even though we don't call it carbon monoxide, we call this thing carbonyl when it's part of a complex ion or a coordination compound. We call this thing carbonyl, but carbon monoxide doesn't have a charge. Carbon monoxide has a charge of 0. So it doesn't matter how many of them we have. If this has a 0 charge, then this must be iron with a 0 charge. And again, I say charge because that's kind of the default for a lot of chemists, but it's really a 0 oxidation state because again, these aren't coming together because of oppositely charged things. They're coming together because the electrons are being shared between the two. So that's the subtle difference between oxidation state and charge. Although in a lot of cases we can use them interchangeably. So the oxidation state of iron, regardless, is still 0 in this case. That is your introduction on coordination chemistry. If you have any questions, feel free to ask. Have a great day, everybody.